Every vehicle begins as an idea. Long before it reaches a showroom, thousands of engineers, designers, and technicians spend years turning sketches into machines capable of carrying millions of people safely every day. Modern cars contain more than 30,000 individual components. Every one of them must work together perfectly, because even the smallest mistake can have enormous consequences. Designing a car is one of the most complex engineering challenges in the world. Manufacturers must balance safety, fuel efficiency, performance, comfort, emissions, durability, and affordability, all within strict regulations and competitive deadlines. A single change to one component can affect dozens of others. Engineering is a constant exercise in balancing trade-offs. Not every engineering mistake is obvious. Sometimes a tiny spring, a software error, or a small manufacturing defect goes unnoticed during development. The issue may not appear until thousands or even millions of vehicles are already on the road. By then, correcting the problem can require one of the largest recalls in automotive history. The automotive industry has learned many of its greatest lessons through difficult experiences. Major failures have led to stronger safety standards, improved crash testing, stricter quality control, and better engineering practices. While some mistakes carried enormous financial and reputational costs, they also drove innovations that have made today's vehicles significantly safer. In this documentary, we'll examine some of the most influential engineering failures in automotive history, from controversial fuel tank designs to faulty ignition systems, to one of the largest airbag recalls ever recorded. These stories changed how cars are designed forever. By the late 1960s, American drivers were looking for something different, smaller, lighter, and more fuel-efficient cars. Foreign manufacturers were rapidly gaining popularity, and U.S. automakers faced intense pressure to respond. Ford introduced the Pinto, a compact car designed to reach the market quickly and compete in a fast-changing industry. Creating a compact car meant working within strict limits. Engineers had to fit the engine, suspension, passenger cabin, luggage space, and fuel system into a much smaller body than traditional American sedans. One of the design decisions placed the fuel tank behind the rear axle, an arrangement that later became the subject of intense public discussion following certain rear impact collisions. The case highlighted how packaging decisions can influence safety performance. As reports of severe rear-end crashes emerged, public attention intensified. Safety investigators, engineers, journalists, and regulators all examined the vehicle's performance. Crash testing became more sophisticated, and researchers worked to better understand how different impact speeds and structural designs affected occupant safety. The debate extended far beyond a single model. It prompted a broader conversation about automotive safety standards. The controversy encouraged major changes across the automotive industry. Manufacturers strengthened fuel system protection. Rear structures were redesigned to absorb crash energy more effectively. Fuel tanks received additional shielding and improved placement in many future vehicle designs. Governments also expanded safety regulations and testing requirements. The lessons influenced vehicles far beyond the Pinto itself. Today, modern vehicles undergo extensive crash testing before reaching customers. Computer simulations evaluate thousands of impact scenarios. Physical crash tests verify those results. Every improvement reflects decades of engineering experience. And every lesson, however difficult, has contributed to making today's cars safer than ever before. Some engineering failures don't involve engines, or brakes, or transmissions. Sometimes, the smallest component can become the most important. Inside every vehicle is an ignition switch, a device that allows the engine to start and keeps critical electrical systems operating. It seems simple, but its reliability is essential. In certain vehicles, investigators found that under specific conditions, the ignition switch could unintentionally move out of the run position. If that happened while the vehicle was in motion, the engine could shut off. Power steering and power-assisted braking could become more difficult to use. Depending on the circumstances, other safety systems, including airbags, might also be affected. This combination of events made the issue especially serious. Regulators and safety experts began an extensive investigation. Thousands of documents were reviewed, vehicle testing was repeated, design specifications were carefully examined. The goal was not only to understand what had happened, but to ensure similar problems could be prevented in the future. The investigation highlighted the importance of rigorous engineering reviews and timely reporting. Once the issue had been identified, a large recall program was launched. Owners were notified. Dealerships replaced affected ignition switch components. Manufacturers strengthened internal safety review processes. The case also influenced how engineering concerns are escalated and evaluated across the automotive industry. It became a reminder that even a very small mechanical part deserves the highest level of attention. Today's vehicles are developed with additional layers of testing, verification, and quality control. Engineers simulate years of real-world use before production begins. Every design change is carefully documented. Every critical component is repeatedly evaluated. Because in automotive engineering, there are no small details. For years, diesel engines were praised for their fuel efficiency and strong performance. Manufacturers promoted them as a practical solution for drivers who wanted long-range capability and lower fuel consumption. Sales grew rapidly across many markets. But behind the success, emissions regulations were becoming increasingly strict. Meeting those standards without sacrificing performance had become one of the industry's greatest engineering challenges. During emissions testing, investigators discovered that certain vehicles behaved differently in laboratory conditions than they did during normal driving. The software could recognize testing situations and adjust engine operation accordingly. The findings shocked regulators, engineers, and customers around the world. Authorities in multiple countries launched extensive investigations. Millions of vehicles were reviewed. Manufacturers updated software, modified emissions systems, and expanded compliance programs. The scandal led governments to strengthen testing procedures, introducing more real-world driving evaluations rather than relying solely on laboratory tests. The way emissions were measured changed dramatically. The automotive industry responded with major investments in cleaner technologies. Engineers developed improved exhaust after-treatment systems, more sophisticated engine controls, and advanced emissions monitoring. At the same time, many manufacturers accelerated research into hybrid and electric vehicles. The crisis reshaped the future of automotive engineering. Technology alone is never enough. Successful engineering also depends on transparency, testing, and accountability. The diesel emission scandal became a reminder that innovation must always be matched by integrity. Today's vehicles face stricter testing than ever before, and those lessons continue to influence every new model built around the world. By the late 2000s, reports from drivers began drawing significant public attention. Some described unexpected vehicle acceleration under certain circumstances. Safety agencies, engineers, and manufacturers immediately began collecting information. Every report was carefully documented, because when driver safety is involved, every detail matters. Engineering teams launched one of the most comprehensive investigations in modern automotive history. Vehicles were inspected, electronic systems were analyzed, mechanical components were tested repeatedly. Investigators examined accelerator pedals, floor mats, braking systems, and electronic controls to understand every possible contributing factor. The process required years of technical analysis. As evidence developed, large recall campaigns were introduced for affected vehicles. Dealerships across multiple countries worked around the clock. Technicians replaced or modified accelerator pedal components where required. Floor mats were redesigned or replaced in certain models. Software updates and additional inspections were also carried out where appropriate. Millions of customers brought their vehicles in for safety improvements. The investigation influenced vehicle design across the industry. Brake override systems, which reduce engine power when the brake and accelerator are pressed together, became increasingly common. Manufacturers strengthened quality control procedures. Electronic monitoring systems became more sophisticated. Testing protocols expanded to cover an even wider range of real-world scenarios. Every lesson pushed automotive safety another step forward. Today's vehicles are monitored by hundreds of sensors and millions of lines of software code, yet engineers continue searching for potential weaknesses before customers ever drive a new model. Because in automotive engineering, success isn't measured by how fast a car can go. It's measured by how safely it protects the people inside. The biggest mistakes in automotive history changed how cars are built forever. Today, engineers don't rely only on physical prototypes. Before a single bolt is tightened, entire vehicles are created inside powerful computers. Every crash, every vibration, every extreme temperature, every component can now be tested virtually long before production begins. Artificial intelligence has become one of the most valuable tools in automotive engineering. AI can analyze millions of design combinations in hours. It identifies weak points that human engineers might overlook. By predicting potential failures before a vehicle is built, engineers can improve durability, reduce recalls, and increase safety. Technology isn't replacing engineers. It's helping them make better decisions. Modern vehicles experience thousands of crashes without ever touching a wall. Digital crash simulations recreate frontal, side, rear, rollover, and pedestrian impacts. Engineers study how every panel bends, how every airbag deploys, and how every seatbelt protects passengers. Only after passing countless virtual tests does a real prototype move to the crash laboratory. Factories have become smarter than ever. Sensors monitor production equipment around the clock. Machine learning systems detect tiny manufacturing changes before defects appear. Some manufacturers can even predict when a robot or machine will need maintenance before it fails. The goal is simple: prevent problems instead of fixing them later. Modern engineering is built on every lesson learned over the past century. Each investigation, each redesign has helped create safer vehicles for millions of drivers, and the next generation of cars may become the safest machines ever built. The modern automobile has evolved far beyond a mechanical machine. Today's vehicles contain dozens of computers, hundreds of sensors, and millions of lines of software code. Many safety improvements no longer require replacing physical parts. Instead, manufacturers can deliver software updates that improve vehicle performance, efficiency, and safety throughout the car's lifetime. The automobile is becoming smarter every year. One of the biggest changes in automotive engineering is the ability to improve vehicles after they leave the showroom. Over-the-air software updates allow manufacturers to refine braking systems, battery management, driver assistance features, and infotainment systems without requiring many owners to visit a dealership. This represents one of the most significant engineering shifts in automotive history. Advanced driver assistance systems are already preventing countless accidents. Automatic emergency braking, lane keeping assistance, blind spot monitoring, driver attention monitoring, surround view cameras. These technologies continuously observe the road, helping drivers react more quickly to unexpected situations. While no technology can replace attentive driving, these systems add valuable layers of protection. Looking back, the industry's greatest engineering failures also became its greatest teachers. Each recall, each investigation, each redesign improved manufacturing, strengthened regulations, inspired new technologies, and encouraged engineers to ask a simple but powerful question: how can we make tomorrow's car even safer than today's? Perfection may never exist, but progress never stops. Every new vehicle carries decades of engineering knowledge built from both success and failure. The biggest engineering mistakes in history left a lasting legacy, not because they were mistakes, but because they inspired the innovations that continue protecting millions of drivers around the world.